Integer factorization decomposes a number into a product of smaller integers. If the smaller integers are prime numbers, then the process is called prime factorization. In other words, if p and q are prime numbers and n is equal to the product of p and q, the prime factorization takes the input n and outputs p and q. While given p and q, it is easy to multiply p and q to derive n. It can be difficult to compute the prime factorization, especially for large n. RSA assumes that it is difficult to computationally solve the prime factorization problem given a large n. That is, while n can be publicly known, p and q are kept private, because it is difficult to derive p and q from n. In fact, p and q are only used for the key setup and nothing else, meaning p and q are only used within the user generating the key, and does not appear in the RSA encryption and decryption processes. From p and q, the public key E and the private key D are derived, and these keys are used for the encryption and decryption, where M is the plaintext and C is the ciphertext. In addition to p and q, which never leaves the user generating the key, D, the private key, is also private and is kept only to the user generating the key. This is in contrast to the public key E and N, which acts as the modulus, which can be public. In this module, we will first describe the encryption and the decryption processes given the public-private key pair and the modulus N. And then we will describe how those public-private key pair is generated from P and Q.